Okay, so you know how we've been talking about the standard model of particle physics?
Right, like the foundation of how we understand the universe at its most basic level.
Exactly. And it's been incredibly successful in explaining so many things, but there are still some pretty big mysteries out there that the standard model just can't quite explain.
Yeah, like dark matter and dark energy, for example.
Yeah.
Huge parts of the universe that we know are out there, but we can't see them or explain them with the particles we already know about.
Exactly. It's like we're missing some of the pieces to the puzzle. And that's where the idea of hidden particles comes in.
Hidden particles.
Yeah.
So, like secret ingredients to the universe that we haven't discovered yet.
That's a great way to put it. These are particles that are thought to interact very weakly, if at all, with the matter that we can see and study directly.
So they're like ghost particles, passing right through us without us ever noticing.
Kind of. And the paper you shared about the SHiP experiment at CERN dives deep into this idea of hidden particles. It's like they're trying to build this incredibly sensitive experiment to catch these elusive particles in the act, if they even exist at all.
Okay, so let's talk more about that. What makes these hidden particles so difficult to find in the first place?
Well, their defining characteristic is their weak interaction with the known forces and particles of the standard model. They don't play by the same rules, which is why they're so hard to detect using our conventional methods.
So if they interact so weakly, how do we even know where to begin looking for them? It seems like searching for a needle in a cosmic haystack.
That's where things get really interesting. Physicists have proposed various theoretical frameworks or portals that connect the standard model to these hidden sectors. One of the most well-studied portals is called the vector portal.
A vector portal. That sounds like something out of Star Trek. Does this portal lead to a hidden dimension of particles?
It does sound pretty sci-fi, doesn't it? But in essence, this portal describes a way for these hidden particles to interact with our world through a new type of force-carrying particle.
Okay, so a new fundamental force. That's a pretty big deal.
It is. And one of the leading candidates for a particle that might mediate this interaction is something called a dark photon.
A dark photon. So is that like a shadowy twin of the regular photons that make up light?
That's the idea. It would be like a heavier, hidden cousin of the photon. It wouldn't interact with our eyes the way regular photons do, but it could still exert a subtle force on other particles.
So by studying these subtle forces and looking for deviations from what we'd expect based on the standard model, we might be able to catch a glimpse of these hidden particles.
Exactly. And the SHiP experiment is looking for exactly that. But they're not just looking for dark photons, they're also looking for another type of hidden particle called a heavy neutral lepton, or HNL for short.
Okay, heavy neutral leptons, H and Ls. Those sound intriguing. What makes them so interesting to physicists? And how do they fit into this whole hidden particle picture?
Well, one of the things that makes HNL so fascinating is that they could be related to one of the most abundant yet mysterious particles in the universe, the neutrino.
Neutrinos, right. Those are the ghost-like particles that can pass through light years of lead without even slowing down. What's their connection to these H and Ls?
The connection lies in a mind-blowing concept called the seesaw mechanism, which suggests that the extremely small mass of neutrinos could actually be a clue to the existence of much heavier particles, the
Then go ahead.
HNLs.
The seesaw mechanism. Okay, you're going to have to break that down for me. How can the lightness of neutrinos be a hint that something much heavier exists?
I know, it sounds counterintuitive, right? So it's like this. Imagine a seesaw, right? One side goes up, the other side goes down.
Okay, I picture that.
So in this case, the neutrinos, which are incredibly light, would be on one side of the seesaw, and on the other side, you'd have these much heavier HNLs.
So the existence of these super heavy H and Ls could actually explain why neutrinos are so light. They're balancing each other out.
Exactly. The lighter the neutrinos are, the heavier those HNLs would have to be to compensate, according to this mechanism.
That's such an elegant idea.
Yeah.
So where does the SHiP experiment come into all of this?
Well, SHiP is designed to be particularly good at detecting particles in the lower mass range, which is where some of these HNLs could be hiding.
So SHiP is like a specialized detective looking for clues in a specific part of the hidden particle world.
That's a great way to put it. And it all comes down to how SHiP is designed. They're using this really intense beam of protons that they smash into a target, creating a cascade of particles. And within that shower, they hope to find some of these hidden particles like HNLs.
It's like they're trying to shake loose these hidden particles by creating a mini chaos of particle interactions.
Exactly. And because these hidden particles interact so weakly, they need a really clever way to actually detect them. That's where SHiP's detectors come in. They're designed to be incredibly sensitive, shielded from all the noise of regular particle interactions.
So they're like these high-tech sieves filtering out all the common particles to try and catch those rare, weakly interacting ones.
Exactly. And here's the thing, even if SHiP doesn't directly detect these hidden particles, the experiment itself could still tell us a lot about the universe and the fundamental laws of physics.
How so? It seems like if they don't find anything, it would be back to the drawing board.
Well, even the absence of a discovery can be informative. The fact that we haven't seen these particles yet, even with these incredibly sensitive experiments, might mean we need to refine our theories about where and how to look for them.
That makes sense. It helps us narrow down the possibilities.
Yeah.
So in a way, even not finding anything would be a step forward.
Exactly. It would tell us that maybe these hidden particles are even more elusive than we thought, which would be exciting in its own right. It means there's more to discover, more to learn about the universe and how it works.
I like that perspective. It keeps things interesting, right?
Definitely. And speaking of interesting, we've talked about how these hidden particles could be connected to some of the biggest mysteries in physics, like dark matter and the matter-antimatter asymmetry.
Right, those are huge unsolved problems. So how could finding these hidden particles shed light on something as mysterious as dark matter?
Well, one possibility is that dark matter, which we know makes up a huge portion of the universe, might be made up of these hidden particles. They could be interacting with each other through their own hidden forces, forming structures and influencing the evolution of galaxies, even though we can't see them directly.
So it's like there's this whole hidden world of particles out there, potentially shaping the universe as we know it. It's mind-blowing to think about.
It really is. And the search for these hidden particles could be our key to unlocking the secrets of this hidden world.
It's like we're explorers setting sail into uncharted territory. Who knows what we'll find?
It really is. It's like we're trying to piece together a puzzle, but we don't even know what the picture is supposed to be yet.
And we might not even have all the pieces. But that's what makes this whole search so exciting, right?
Absolutely. It's the thrill of the unknown. It's like we're pushing the boundaries of human knowledge, venturing into uncharted territory. And who knows, maybe the discovery of these hidden particles will completely revolutionize our understanding of physics and the universe.
It's certainly a possibility. Remember how we talked about those theoretical portals earlier?
Yeah, like the vector portal, the gateway to the hidden particle world.
Exactly. Well, some physicists believe that these portals could be even more profound than we currently understand. There's speculation that they might even connect us to other dimensions beyond our own.
Whoa, other dimensions. Now you're really taking us down the rabbit hole.
I know, it sounds like something out of science fiction, but the math behind some of these theories actually allows for it. It's still very speculative, of course.
Yeah.
But it's a fascinating possibility to consider.
It is fascinating, and it just goes to show how much we still don't know about the universe.
And that's a good thing. It's what keeps us asking questions, keeps us exploring. It's what drives scientific progress.
Absolutely. The universe is full of mysteries, and the search for these hidden particles is just one example of how we're trying to unravel them. It's a testament to human curiosity, ingenuity, and our endless thirst for knowledge.
I couldn't agree more. It's an exciting time to be a physicist.
It really is. Well, we've covered a lot of ground in this deep dive, from the tiniest particles to the largest structures in the universe. We've talked about the Standard Model, hidden particles, dark photons, heavy neutral leptons, the seesaw mechanism, even the possibility of other dimensions.
Quite the journey.
It really has been. So as we wrap things up, I hope our listeners come away with a sense of wonder about the universe and the incredible discoveries yet to be made. The search for hidden particles is just one small part of a much larger story, a story that's still being written.
Beautifully said.
Thank you for joining us on this incredible journey. Until next time, keep exploring the cosmos.